as you are aware that we have assembled here to hear on optical tweezers throwing light upon light by Professor Ayan Banerjee from IISC Kolkata.
IISER.
IISER Kolkata, sorry.
I
IISER
would
Kolkata.
love it had it been in
Yeah,
Kolkata, because then I wouldn't have to go to Bangalore.
Yes. Sorry. So let me introduce about the speaker. Professor Ayan Banerjee is a professor of physics and presently the department chair at IISER Kolkata. He is an experimental physicist working in optics and precision spectroscopy for the last 25 years. At IISER Kolkata, he has set up a laboratory which specializes in optical trapping and manipulation. Research in the lab spans a wide gamut of applications with tweezers, including the spin-orbit interaction of light, micro-patterning using tweezers generated, and manipulated micro-bubbles, non-equilibrium statistical mechanics and stochastic processes, thermodynamic, thermo-optical traps, and so on. He has published more than 50 research papers and 20 patents based on his research. Wow, 20 patents. He has involved with anything creative and it's a co-curricular activity, theater worker and playwright and occasional blogger. So without being an eclipsing object between the audience and the speaker, I invite Professor Ayan Banerjee. Please, Professor Ayan Banerjee.
Yeah, thank you so much for giving this opportunity. I wish I could have actually visited BITS Pilani, physically, because it's a lovely place. I've heard about it right from childhood, and it was like a go-to place for us. It's in Rajasthan. That's also a place I've never been. So yeah, things, of course, hopefully one, sometime down this whatever time, I will actually be able to visit you and talk about things that I like in physics, maybe other things as well.
Definitely.
So, right. So I'll just so I'll just share my screen and
yes, please.
Yeah. Yeah. So can you see my screen?
Yes.
Can you see my screen? Yeah.
Yes.
Okay. Yeah. So today's topic is, as Rakesh had requested me, some time back about. So it's very good that you guys are starting this Nobel Talk thingy, because finally the Nobel Prize is given to, the best endeavors in science, which have a lot of basic science behind them. Not only that, but also which lead to significant applications. And what I'm going to talk to you about today, optical tweezers, which are actually used, the Nobel Prize was specifically given to the application of tweezers in biology, but actually tweezers have a lot of applications in every, branch of science, from physics and chemistry and material science. So our lab actually specializes in optical tweezers, and we actually have projects in almost like every branch of science. In fact, biology is probably the one that is represented the least, but still we are actually starting to work on it. We have a few published papers as well, so I'm going to talk about that a little. But then what optical tweezers have actually facilitated in biology, that has led to a revolution in the study of very, very these small fundamental blocks which actually make up life. So that is what this cartoon actually tells you. So what you have here is a small probe, and what you have here in the background is some diffuse beam of light. It's looking diffuse. It's actually pretty strong, high intensity of light, which is actually tightly focused. Tightly means it's focused to a very small spot, and it holds this small particle here. It's like only a micron, few microns in diameter. And then what you have here is the DNA, and then what I have here is the world. So it's actually the whole entire world represented like a cartoon. So we're actually going to study when we go into the talk, how we can actually hold the DNA between two small particles and stretch them and do all kinds of very, very nice things. So what I have here, however, representing is that, we have a micron-sized particle, which actually gives us information about things that is like, 13 orders of magnitude in terms of length, larger. So you actually know about the macro world through events in the micro world. And that's what I'm going to talk to you today. How we can, so light is an essential component of optical tweezers, and how you can use light to understand life, or more precisely speaking, the building blocks of life. So Arthur Ashkin, the person who discovered tweezers, he got this prize in 2018, and I think 50% of the prize actually. So for fundamentally the work that he had done, of course he discovered tweezers, but then because of, he also initiated some of the first work on with tweezers in biology, and that was the part that was really recognized by the Nobel Committee, and they specified that in the citation for the work in biology. So what we have, just go around. So what does tweezers mean actually? So this is like a DNA molecule, and what you basically so this is a real tweezers, right? So if you have a real tweezers, then of course I'm sure you've seen this object. This is there in biology labs. This is used in daily life quite a bit, used for doing makeup and all kinds of stuff, cosmetics. So that, however, this is like, how big is this? This is what, 3 inches in long. This is a DNA, and that is a single molecule. That's just nanometers. Can this hold this? No way. This we can. So remember, our vision, we can see only, the resolution of vision is only about few microns. Remember, our hair is about 100 microns thick. The DNA is few nanometers, tens of nanometers. So this is invisible as far as we are concerned. So then, can you hold this with this? The answer is no. However, you can actually have a small micro a particle, like, this is like a polystyrene or a silica bead, small, as we call it, probe particle, spherical probe particle that is transparent to this light that is incident on it. And that, however, is able to hold it. And by manipulating the light, you can actually play around with this DNA just as you would for a tweezers in the case of, whatever some macro object that you can think of. Okay, so how is it possible? So light, of course, light is life, right? Finally, if there were no light, this earth, we would all perish, right? But does light have power? I mean, what do I mean by power? So if I go, so when I say power, there is something to do with machines, right? The power to move, the power to do work, power to do work. So if I go out and stand there in the sunlight, do I fall down? Does the sunlight make me run? Of course, I can feel hot and start running. That's different. But can it do anything to me at all? Remember the radiation pressure force, which is like, the amount of actual mechanical, the pressure that, pressure is forced by area. So remember, light actually has photons. So photons have momentum, which I'm going to tell you in the next slide itself. Because there is momentum, there is force, and if there is force, there is pressure. So that means it is about 1360 watts per meter square. This has no effect on us. But if you were a very, very small particle, if you were a particle which is similar or in diameter to the wavelength of light, say 600 nanometers, then you would actually be really, really, kicked around by the light. You would actually, this is force is 1,000 dynes. That is quite a lot, right? And you could actually get accelerated by 10 to the 5 g. This is the acceleration of gravity. Light has enormous power. What does meso mean? Meso is a form which means everything ranging from microscopic to nanoscopic. Mesoscopic is the word which combines nano and meso. Okay, so that is what optical tweezers do. We apply controlled forces on mesoscopic particles, and that is how, because photons have momentum. And how can that be used? So if I have a Gaussian beam, so what does the Gaussian beam mean? So if you think, I'm sure all of you have seen lasers, right? So you've seen a laser pointer. I'm sure in your practical labs, you must be doing diffraction and interference, simple experiments, and there you must be using lasers. So if you just have a laser beam falling on the wall, And if you were to shoot, take a picture image on a camera, and then if you just do a line profile, you draw a straight line in a software or something which can read the image, and then you can plot the intensity distribution of that light across that beam. You will find a function called a Gaussian. I'm sure everybody knows a Gaussian, e to the minus some r squared by some w squared, where w is the beam waist or radius, whatever you say. It's like the waist, not really radius, but it's a parameter of the beam, which is related to the radius. And that means that the Gaussian beam has enormous intensity at the center, and then it falls off, right? That means it actually has a very strong intensity gradient, because the intensity is not constant. It's not like light coming through from the sun through your window or something. It's like a patch of light with no intensity gradient. So what happens is, a particle, when I actually impinge a Gaussian beam on the particle, on this particle which can allow the beam to transmit through it, it can actually be trapped and moved around. And you can apply very controlled forces, which can range from this piconewtons and something. How is this important? Because if you were to look at the gravitational force, inertial force that acts on a particle whose weight, it's like a few picograms to something, that will actually come to piconewtons. You can actually move particles around by a focused Gaussian beam. As a result of it, there are enormous applications right from physics to biology, because you can actually confine particles, you can hold them, you can move them around, you can actually measure the amount of force that you can put on the particle, and you can also measure the reaction that the particle actually provides. That is what they do in DNA and all that. So a simple schematic. This is my Gaussian beam, and this is like how it looks in cross section. This is the profile, and this is how it moves actually in the z direction. This is the transverse, which is like the x and y, and this is how it looks as it traverses. So this is where it's focused. This is called the waist of the beam. And if I have a particle which is here, it's smaller than the beam, this is the beam center. And if you think this refractive index of the particle is actually larger than the refractive index of the medium outside, then this beam here, so this is like, I'm a bit of a, we use this kind of a liberty of, this is a beam, but suppose we're going to think of it as rays. That means if I can say that the number of rays here, or somehow the rays on the center are more powerful than the rays at the side, then if you can see here, this ray sort of gets diverted like this, right? It bends towards the right, because of the refractive index contrast of this particle and the medium outside, and then when it comes out, it again diverts like this. So what happens is, you can say that the particle pushes the light to the left-hand side. This is the left-hand side, right? And the light, on the other hand, then just by Newton's laws, will push it to the opposite side. Just, every action has an equal and opposite reaction. So if the particle pushes the light towards this side, this is the left, then the light will push the particle towards the right, and that's why it goes towards the center. And the center of, and so here also, right, this edge, the ray at the edge, that also does the same. This would actually have an opposite reaction on the particle. But remember, this is much more powerful. There is much more intensity here than here. So the amount of the final reaction force that you get towards the center of the beam, that is towards the right-hand side, is actually much higher than towards the left-hand side. So the particle gets a kick towards the center. Similarly, if the particle tries to go towards this side, it will get another kick towards the left-hand side. And therefore, it will stay in the center. It will just wiggle around. And what this basically translates to is that this particle is like a spring mass system. It is like a ball which is connected to the center by a spring. This spring is called the optical trapping force stiffness. This is like if you have x equal to f equal to minus kr, this is the famous restoring force formula for any linear harmonic oscillator. This is the force stiffness. This is the stiffness constant. And this, as you can understand, is basically the intensity here is much higher than here. And what happens here is actually this force is, one can show by calculation, this is proportional to the intensity gradient, right? So the intensity gradient is actually minimum here. It's much higher here. So the more the particle moves out of the track, it'll actually feel a higher force towards the center. right? And the force at the center, exactly at the center, is 0. And it is, as you move out, it is higher, and it's linear with distance. Very, very important. So when was this first done? It was first done by Ashkin way back in 1970. Physical Review Letters, one of the biggest journals in physics, right? And American Physical Society, this is where it comes out from. So what he showed was that if you have laser light, which is focused in this liquid medium, and you had silica particles falling in, what he actually showed was that these particles, I think there were some 10 microns or something in diameter, then he actually showed that these were levitating, these were feeling some force. He had two configurations. So one was that when he had this beam coming from the side, right, and these particles falling perpendicular, and here, the other way, actually he had two beams, counter-propagating beams. So one thing I didn't talk to you about. So just like here, you have a beam that is transmitted through, you also have something that is reflected off. And think of this, if the particle, the light gets reflected off like this, you will actually have some kind of restoring force towards the direction of the beam. It will try to throw this particle out of the trap. That's called a scattering force. So here so the scattering force is destabilizing. So what he had here is that if you have a beam, so it is in the direction of the laser beam. So what he had here was that the scattering force for this beam is towards that side, and for this beam is towards this side. Then they finally cancel each other. And you can actually also have some kind of, levitation here. Ashkin didn't he saw this, he reported this, didn't do too much. In 86, however, he first talked about this really in detail. We talked about this, single beam radiant force optical trap, as I just said, optical tweezers for dielectric particles. This was where the term optical tweezers was given. And you see range of particle size of 10 micron to 25 nanometers in water. And you can actually see trapping of particles in water here. And this was what launched off this field of optical tweezers. This paper was published in Optics Letters. So this is in terms of importance. So, I don't know whether you guys are aware about this term called impact factor. So that is what drives scientific publication these days. So it essentially means how many times a paper that is published in a journal, how many average citations it gets. So in that way, PRL, Physical Review Letters, has an impact factor of about 9.5. Optics Letters is about 1/3 of that. And yet, this paper has been cited more than 10,000 times. So again, for people who would be physicists, impact factor doesn't really tell you too much. If your work is good enough, it will be picked up by the community. And finally, that is the judge of how good the work, how important the work is, right? So this was the first time, 1986. So what can you do? What are the measurements that are actually facilitated? So one can understand, though, I told you that the force felt by the particle due to the light is 0 at the center. But does it mean that the particle is stationary? It's not. So what I did not tell you then, I probably said when I talked about Ashkin's work, is that these particles that he was trapping were immersed in water. So if you have a particle in water which is very small, where there is enough buoyancy, then the particle does not go and settle down at the bottom of the vessel or whatever sample chamber that you have the fluid in. It actually undergoes Brownian motion. So even inside your trap, where the force due to the light is 0, the particle is not stationary. It actually undergoes Brownian motion. Now, Brownian motion means what? Collisions with the water molecules and all, and get random kicks. It's very, very random. It gets kicked around. Problem is, if it gets a kick and it goes out from the center of the trap, then it will immediately feel a force from the trap back to the center. So if the trap is very steep, remember, if your force is equal to minus kx, the potential is kx squared, which is again like, it's like a potential well, right? So that means that if your potential well is very steep or the stiffness is very high, then the Brownian motion amplitude will be small. A very, very small amplitude of Brownian motion, the particle field will immediately get kicked back. So we have the particle jittering around very fast jitter. If the trap is weak, which means that K is small or the potential well is not steep, it is shallow, then the particle can migrate a lot of distance from the trap before it actually gets a kickback. So the amplitude of the Brownian motion actually enables you to understand how strong the trap is. So this is called, the trap stiffness. You can directly measure from the Brownian motion of the trap. That is typically measured by, measuring the light, that by detecting the intensity of the light that is scattered from this trap particle. Because, the scattering light, as I told you, it's not useful for trapping, but it's very useful to understand the position of the trap particle. So because if the particle moves, remember, the scattering intensity changes, the intensity profile changes. And you have some detectors. You can either do this by a camera, which can actually show you how the particle moves. So if you have a fast camera where you have many, many frames per second, then you can, take a video recording, break that recording into frames, and actually find out the displacement of the particle very accurately. And you can construct something called, if you go to frequency domain, it's called the power spectral density, something. Anyway, from the displacement, you can find out the details about the trap itself, how stiff it is, how strong it is. Essentially, the K is large, stiffness is large. So other ways that you do it is by something called a quadrant photodiode. So remember, what is a quadrant photodiode? It is so typically you have photodiodes, right, which help you measure the intensity of light. The problem with photodiodes is they just measure the intensity. They do not tell you. So if wherever the light falls on the photodiode, the signal will be the same because it integrates all the signal from the photons that are excited. That is how a photodiode works. However, in a quadrant photodiode, what you actually have is the photodiode is divided into 4 different areas. Each of them give you, or quadrants as they say, and each of them give you different signals. And if you subtract the signals adequately, you can measure the displacement of the particle. And the displacement of the particle actually tells you this x, and you can actually get kx by some methods. I'm not going to go into details. If you want to read about how tweezers are actually made or done, the basic, sort of how to construct a tweezers, I will point you to some papers. What is important, however, is that you are able to exactly measure the force that the light actually applies on this particle, right? So what is typically done for biology, you take and tether, that is, you connect this DNA, whatever, to this particle, and you can, by pulling this particle by the light, you can actually stretch the DNA. The DNA, is like an elastic entity, and it will also pull back, and that's very nice. You have a tug of war, right? So basically, this is what is done. So there are many, many sort of applications, many, many configurations here. So what we have, for example, this is like a plate which is connected, which is sort of the surface of this is essentially functionalized. That is, you put some kind of a coating here where you, for example, you can put biotin and you can put something like streptavidin, some kind of a, two things which attach to each other. And then you basically have this DNA also attached to this small thing here. Okay, some kind of a microtubule, anything of that sort. And the one end of the DNA is attached to this plate, to this thing. And here, the other end is attached to this particle. How does this bead or this DNA attach to this particle? You actually functionalize this bead. So you have some kind of a molecular attachment. You functionalize this bead, this particle, this called this probe with something, some agent with which the DNA at a molecular level, it just adheres, right? And then this whole thing becomes like 2 springs that are attached to each other. You have the elasticity of the DNA and you have the elasticity of the trap. Remember that K. So you have a K DNA and a K sort of a trap, and the displacement of the DNA and the displacement of the trap. And you can actually do essentially just pull this DNA gets sort of extended. It itself tries to relax. So what you have, if you measure it, if you give the force by just moving this bead, and if you see how much this gets displaced from the center because of the pull of this DNA, you can actually build these force extension curves. And like, when this is essentially, this is some kind of a linear response of the DNA where it follows a Hookean region. Here it gets nonlinear. These are different forces, different domains. And here again, it becomes nonlinear here. So the other thing that is done, this is very important, it's called a force clamp. So what is done here, you have two particles, and this is telling you, this is what is this. So remember, if I take, if I showed you, I told you the potential is like kx square, the force goes like minus kx. But remember, the force was also proportional to the gradient of intensity. If you can take a profile of the force, line profile versus x, then you will get something like this. Okay, you get something like an error function. This is called in physics, where this part is linear. This is like a restoring force. This is zero force, and the particle goes here, it will feel a force again towards this part. If it goes here, again gets a force back. So you see, this is like, there are two traps here. This is a steep trap, this is a shallow trap. You see, this particle, this second trap is placed here. And at this point, the force is constant because the gradient of the force is zero, right? The gradient is zero here. So if you have this DNA, which is attached to two different particles, okay, both are functionalized at a molecular level, DNA is attached between these two. Here, the force that the particle, the trap employs of the DNA is zero. So you measure the displacement here, and this one is a very strong trap. You set the force, you measure the force here, right? So if you basically pull this somewhat, this one moves, and any effect of the DNA is felt on this particle, right? Because the trap exerts no force on this bead. This is on a zero force region. This is in a high force region. And therefore, you actually build this force extension curve. You apply certain forces here. The DNA sort of is displaced, and that you basically measure on this, and this is the displacement, this is the force. This is where you keep on pulling. This is the Hookean region of the DNA. This, however, is where the DNA basically goes to nonlinear. Here it sort of breaks down. It does not have any conformational changes back to its original shape. Here it breaks down. This is like a non-linear region. So what are my different configurations? So this is a very important paper. I don't see the reference. Okay, whatever. So the reference here is somewhat missing. So this is a paper that just came out in 2021 in Nature Methods by Carlos Bustamante's group. So just do a search in Nature Methods. This is very recent, by, as I said, Bustamante of California, who actually sort of has a very, very big group in this. So in this optical tweezers biology. So these are the different configurations. So this is what I showed you. This is like, we have a plate here. This is like a cover slip or something. Cover slips, I'm sure you've seen in optical, any microscopy. There are these microscope slides. There are these cover slips, very, very thin. And why do they have to be very thin? Because one very important thing in tweezers, which I did not tell you, is that I need to I see the gradient of intensity has to be very large, right? If remember, because the force is proportional to the gradient of intensity. So how will you make the gradient of intensity large? By making the focal spot very small, so that the intensity at the center is very large. Remember, intensity is basically power divided by area. If the area is very small, power is the same, intensity is very large. So if I make the focal spot very small, I get a very large intensity, and that's if the intensity is very large. Just give me a second. Intensity is very large, then at the sides it falls off very fast too. So the gradient is very large. So that's why typically tweezers they are built around microscopes. And you have a microscope objective. Objective lens means it's about 100x. You've heard about that, right? That tells you magnification. 100x, 30x, 40x, 50x. So 100x microscope means a microscope objective lens. Essentially means that the focal spot is very small, to the order of microns, right? And microns means single 1 micron, something like that. And therefore, what happens is this particle is trapped by, it's trapped. So this thickness of this cover slip has to be very, very small, because the beam, the focal length of the lens of 100x lenses is extremely small, typically 200 to 300 microns. So typically, when we have these lenses in your lab, they're 25 mm focal length, or 50 mm, 100 mm. For a 100x objective, that is only 300, 200 microns, like that. Okay. So what happens is, so here this is a configuration where this as they say, where this molecule is basically attached to a trap bead. And this is part is functionalized, and this is held like this. This is the two trap thing that I said. Again, extension. This one is very nice. We actually have this DNA which is tagged by some dyes, as a result of which, when you have a wavelength of light that is actually corresponding to the dye resonance frequency, you will actually have fluorescence. So from this, you can know conformational changes of the DNA or something of that sort even better. So this is like you parallelly do fluorescence spectroscopy and trapping. Beautiful. This one is even more interesting. This is something called total internal reflection microscopy. So total internal reflection essentially means that you might be knowing that in a prism, if you come from, if you shine light from below, then if you keep on increasing the angle of incidence, at times you will say after a certain angle, you see the light will not leave the prism. It will not get out of the prism. It will get reflected back. If it gets reflected back, the problem is that because the laws of physics tells you that electric fields cannot just disappear. They cannot disappear. So the tangential component of the electric field has to be continuous. So you actually have a small intensity. There's no energy flow, but a small intensity that leaks out. Small, rather, electric field that leaks out, not intensity. Because the electric field leaks out a little bit, and that spatial extent of that field is very small, of the level of hundreds of nanometers, right? What you have is enormous high intensity here, very, very high intensity. And you can actually trap, very small particles here. And that is called total internal reflection microscopy, which is coupled with optical tweezers. So that can, what is the advantage? That you can actually have very, very small particles being trapped, which can actually help you, because the smaller the particle, the more effect it will feel from the DNA, right? It will move about. So if you have a big particle, then the displacement because of the DNA action will be smaller. If you have a very small particle, it will move much larger, right? So you get much more signal to noise. Confocal means what? You basically, confocal microscopy is essentially where you get information about a single plane. Okay, you can actually get, so basically this is the z-axis. So you can actually make, and these are the xy. So in confocal microscopy, you can actually make 3D images, three-dimensional images of this whole system. You can actually trace out this DNA, how the conformation of the DNA in 3 dimensions, which is fantastic. What is this? This is angular optical tweezers. That means what? So light, just as it carries linear momentum, it also carries angular momentum. And remember, a DNA is like a double helix. It is twist. So we can also think of, there is this famous phenomena associated with DNA about, DNA coiling, protein folding, DNA coiling, uncoiling. So torsional properties of DNA. What is, because this is like, this is a double helix, like, so it wraps around each other. So you can actually find out how the DNA acts in terms of that wrapping around itself. So what happens is you can actually have an optical, this light, which has some circular polarization. So light has angular momentum. It's called spin. So polarization, you must be aware of. It can be linear, it can be circular. If you have circular polarization, the light actually has spin. And it can actually, if you put these cylinders or these birefringent particles, birefringence means there's a refractive index gradient inside them, and they can actually interact with light in terms of transferring angular momentum back and forth. So these can actually spin. We can actually make this cylinder spin because of the circularly polarized light, right? And this can twist and untwist. You can measure both the translational and the torsional properties of the DNA. Okay, so these are the configurations, the things that you can do about twisting and untwisting of the DNA. You can find out how a DNA folds, unfolds, all kinds of things. Now we come to the next fantastic thing, kinesin. What is kinesin? This is actually can you believe this, guys? This is a protein. It's a molecular motor just actually walking. What is this? This is like a microtubule. What is a microtubule? Microtubule, so cell, it has a cytoskeleton. So the cytoskeleton is what gives the cell its actual form. And the molecular motors, what are molecular motors? So these are essentially something which induces movement in our body. When I move my hand, it's actually millions and whatever billions maybe of molecular motors which are working in tandem. So how they walk, how they sort of go around, that you can unravel using tweezers. So what is kinesin? This is actually a molecular motor. So there are actin, there is myosin, there is kinesin, all kinds of things. And these have diverse kind of importance, they're in knowing about them. Cellular processes, what have I written here, transport, cell division. If you find out that there is a difference in the walk from normal kinesin, there's a diseased condition. And also, kinesins are targets for cancer treatment in the sense that they are early indicators of cancer. If there is something wrong in the way kinesin is walking, you can see maybe the cell division, there is a problem. Cancer is all about metastasis, right? Cell is dividing wrongly. We can know about that. First observation. Again, first Nature paper on this was Ashkin. However, the first big paper came when by this group, Stephen Bloch's group, a very, very big group in Harvard Medical School. I think, this is Cambridge, Massachusetts. So this paper, what is this meaning? So essentially what it means is so you again do the same thing. You actually, like I showed you in this previous piece of work, where you have this kinesin. So just like, let me come here, go back to this. Oh, sorry. Yeah. So you see one end of the kinesin is attached to a particle. This is my trap particle. And this end is free on a microtubule. And the moment you have kinesin that is fixed on the microtubule, it starts walking because that's the way it's programmed to. And that means what? This particle starts, feeling a force. This trap bead gets sort of feeds a force, right? So this is actually not a bead. This is a cellular thing. So instead of this, if I had a trap probe, a particle, this is under tweezers. One end of the kinesin, these are attached to this bead. This one is on the microtubule. So the moment the kinesin walks, this bead will get displaced. And when it gets displaced, the trap will pull it back, right? And this is exactly what you have. So you have constant force, and then suddenly the kinesin sort of pulls it too much, and you get a jump. Again, you keep doing this. Again, if the kinesin pulls, you get another jump. So essentially, again, you measure a force, a distance, versus a sort of a time thing. This is a distance versus time. And by looking at the small jerky motions of the bead, of this trap probe or something, you can actually find out the steps of the kinesin. This was fantastic, okay? And however, now what has been found is kinesin just does not walk straight. It actually twists and also walks. That is fantastic, right? So if you see again, if I come back, so this is what it does. This is your trap probe, and this is functionalized with so you see, this is nicely rotating. This is nicely rotating. Let me go back again. So this is rotating. So it's like it twists, walks, twists, walks. This was not known. This was first known in 2017. And this guy, Basudev Roy, he happened to be my first graduated student, PhD student. He's in IIT Madras now. And they found it out. They reported this. He did this in postdoc. They reported in this PNAS, a very, very big journal. So this is how kinesin actually walks. It actually does not just walk in a translational motion. It rotates and walks. So how did they find out about rotation and translation together? I showed you about that angular motion thing, right? You have a cylinder. When you bring in circularly polarized light, the cylinder twists. However, you can do the same with birefringent particles. What is birefringent particles? As I said, something which has a refractive index gradient inside. So what happens is when you actually put in circularly polarized light or light carrying spin, the particle starts spinning. And because of when it starts spinning, if you actually have crossed polarizers, in the sense you have a polarizer at the input, a polarizer at the output, then when you actually when your particle, I mean the scattered light that is coming from the particle, when it is along the axis of the polarizer. You know that when you have, say, polarized light and you have a polarizer which is perpendicular to it, of the axis of the polarized light, you'll have no light outside, right? So now here you are actually having scattered light that is coming from this particle. And then you have at the output, rather, not input, output, you have two polarizers, one which renders it linear and the other that is perpendicular. Now, if you actually, because of the circular polarization, you know, when it is treated by a linear polarizer, the resultant light becomes linearly polarized. So what happens is, if I have this input circularly polarized light, once I make it linearly polarized by my polarizer, if the other polarizer is perpendicular, right? If the output from the first polarizer is in the direction of the second polarizer, I get no light. If it is in the direction, if it is perpendicular, or rather, I messed that up. If the polarizer output from the first polarizer is perpendicular to the second polarizer, I get no light. If it is in the direction of the second polarizer, I get full light. Now, when the particle rotates, the output polarization changes. Okay, so the function, as a function of my intensity modulation at the output of my two cross polarizers, I can find out how the particle is rotating, right? So as this particle is rotating, the polarization of the output light is changing, and I can map the intensity fluctuation thus achieved to the rotation directly, and this is what I get. So here you can see I actually do, this is like a time thing. So when you, x-axis is time. So first I get the particle at like 45 degrees. After that, at 45 degrees, at this point, there is nothing, the intensity is constant. Then what I do is I shut the trap off, right? The moment I shut the trap off, what happens is the kinesin, because it's walking, it essentially rotates the bead itself because it is twisting as well. The kinesin is twisting and walking. So now the bead, the particle, my probe particle, is actually going to rotate because of my kinesin walk or kinesin twist. As a result, my polarization at the output will again change and my light intensity will start increasing again. Okay, so essentially think of this. How do I understand translation? By, just as I said, the scattered intensity from the light. This is, so here, this red light is the scattered intensity when the kinesin walks straight, and this blue light is the intensity fluctuation which happens when the particle rotates. Okay, so as I said, there's a quadrant photodiode. Quadrant photodiode does what? There is a detector which is divided into 4 parts. Each of the parts give you different signal, which you can measure. If you take a difference between the two signals, you get information about X. If of the 2 quadrants in specific ways, you can get X motion or you can get Y motion. You get displacement of the particle. And essentially these drops mean that the trap pulls it back. When it goes too far, the trap pulls it back, and essentially the microtubule gets disattached, sort of it detaches. I'm sorry, the kinesin gets detached from the microtubule. So think of it, the kinesin is walking. Because of that, the bead is getting pulled. And at some point, the kinesin, because the bead has been displaced too much, it goes back to the trap. Right? It goes back to the kinesin, sort of detaches from the microtubule. But again, the kinesin wants to, so 1 foot gets detached. So you see, as you remember, the kinesin actually has like 2 feet, right? 2 feet. 1 foot gets detached. It soon gets pulled back. And this rotation, what is what? It is, again, you wait for till it's 45 degrees, trap off, it again will evolve. So this is the trap off, then trap on, goes back to 0. So this blue light gives you rotational signal, this red light gives you translational signal. Okay, last part of the talk, that is a very different type of thing that I'm talking about. Let me just preempt that. So essentially, this, what I talk to you, is about different biomechanical events which we can measure by tweezers. First, we talked about how DNA gets pulled or twisted and all kinds of things. Then I told you about these molecular motors, which move, which walk. And when they walk, essentially those are the things which I'm moving my hand while I'm talking. If this were physical, you would have seen me. My hand is moving because millions of molecular motors are actually walking, right? So that you can pick up. You can pick up step sizes. So you can see this translation. Can you read this? Nanometers. You are actually measuring things like minor whatever. This is in translation means this is, opposite direction. So 48 to 96, 50 nanometers you can measure. Each step size is about few nanometers resolution. Few nanometers I can measure with this. Remember, 100 microns is your hair. Remember realize what you're measuring. Okay, and rotation, this is 20 degrees. So this is like the one with resolution is like milli-degrees, hundreds of milli-degrees order, right? Okay, so now I'm talking about a very, very different thing. Very different things. There is something. So I told you that when particles get trapped in water, right, they move around, right? Now there's Brownian motion. Now suppose, so how are liquids characterized? So if a liquid is very dilute and if a liquid is not dilute, it's very thick, what changes? There's something called viscosity. What is viscosity? It is the amount of friction, a frictional force that the liquid exerts on any solid that is embedded in it. So if the liquid is dilute or something, if it's like less viscous, then it's like friction, right? So if my Brownian motion, from studying my Brownian motion of the trap, so if I want to understand viscosity, okay, if I want to understand viscosity, how do I do that? And viscosity at very, very small points of the liquid. What will I do? I will take a trap by tweezers. I'll take a small particle. I will trap it in some part of the liquid. Now remember, if the viscosity of the liquid is very large, then it will damp down the Brownian motion very fast. If the viscosity is small, then the Brownian motion will actually continue for a very long time, right? Because viscosity is a dissipative force. So now from the Brownian motion itself, I can find out about the viscosity of the particle, of the liquid. This is something called, so viscosity measurement is called rheology. This is called microrheology. Okay, and why is this important in a biological context? Because cells have something like a liquid, some kind of if they have plasma inside or something inside, right? And these essentially are liquidy. These are not completely liquid. This is not like water. Does not like water. They are different. So, for example, do you think of, say, so if you know rubber trees, right? So if you sort of tap at the wood, the bark of a rubber tree, you get a sap out, and that's very viscous, thick, right? It's translucent. That is actually not like water. There is a bit of solid also inside that. These are called viscoelastic fluids. And where am I coming from? I'm saying that the cell environment is filled with a fluid which is actually viscoelastic, which is not like water, which is viscoelastic. And if I can understand, if I can measure this viscoelasticity of the fluid, I can actually measure the cell environment. I know that a normal cell has a certain viscoelasticity. If the cell is diseased, then the viscoelasticity will change. So if I put a small probe inside the cell, or if I make a solution of the cell, so dispersion of the cells, many cells which are inside some buffer solution or something. If I measure the viscosity, viscoelasticity of that solution, then if the cells are all normal, I will measure a certain viscoelasticity. If the cells are not normal, I'll measure a different thing. This is where I'm coming from. This is called, this is something we did in our lab. This is about this sort of class of entities called lamins. What are lamins? These are, again, nucleoskeletal proteins that basically stabilize the structure of the nucleus. So essentially, if your cells have become very stiff, then there is a lot of laminae. If becomes a squishy, soft cells, these are less laminae. These are both diseased. Both are diseased, right? The normal cells have a certain stiffness. Cells are like squishy, spongy materials, right? They have a stiffness. If they get too hard, what is the problem? You can so if your heart cells, if they get too hard, if the heart muscles become inflexible, you may have a heart attack. If the cells get too squishy, that actually may mean there's a tumor growing, which might mean malignancy. Okay? So lamins are some entities which actually can lead to the stiffness of the cell changing. Stiffness means the cells get hard or soft. How can I use optical tweezers to understand this? Because remember, this is finally all to do with the movement of this probe particle that I have. If my environment is very, very, stiff cells or something, then this probe will move in a certain way. If the environment is filled with squishy objects which are very soft, this probe will move in a different way, right? So this is what I'm talking about. What is viscoelastic fluid? This has a viscous and an elastic nature. Okay, this is a bit complex. So what does elastic nature actually mean? Elastic nature means that, essentially, water has all these molecules, right? It's all clashing against each other. Now, the problem is if they're all randomly crashing, then the movement of the molecule at a certain time is completely uncorrelated with its movement at a later time. But if there is some kind of elastic material, then the movement of one time is completely going to dictate the movement at later times. And this is why it's a solidus form, right? So if you change a squishy object, say something, rubber or something, you sort of press it. After some time, it just comes back, right? So it has shape memory. It remembers the shape. Why? Because the molecules, the molecules which are getting sort of affected at a time t dash, which is before time t, the state of the molecule at t dash is remembered at time t. These are viscoelastic materials. There's an elastic nature G, there's a viscous nature eta. And most biosamples like blood cells are all viscoelastic, right? Cream, ketchup, jam, these are the more general fluids. Okay, so now as I said, from the Brownian motion of the cell, I can actually measure this environment of the liquid. Brownian motion of my probe, I can measure the environment in which the probe is embedded. That is the viscosity of the liquid. There are two ways in which you can do this. You can do something called passive, where this just is jiggling around, and from this Brownian motion itself, I can measure. However, remember, this Brownian motion is how big is it? It is only few hundreds of nanometers. So the displacement signal is very, very less. There is another way where I move this trap itself. And so if the viscosity of my environment of the liquid, of the liquid environment I have is very large, then given some kind of amplitude or some way I'm forcing the trap, okay, with the same amount of force in a more viscous liquid, I can move less. So basically, from the response of my trap particle, I can find out how viscous my environment is. The big advantage of this is, see how much this is moving. This is much more than here. I'm actually forcing this. So I'm not forcing. This is like a forced harmonic oscillator. This is like a free harmonic oscillator. Of course, difference between harmonic oscillator in air and liquid is there is no effect of the mass, no inertia. Okay. So basically what I do is I can put some kind of a way of moving my tweezers around. I'm moving them. I can move them sinusoidally. I can move them like in a square wave. Square wave means it jumps to a point, stops and jumps back. Jumps, stops, jumps back. Sine wave keeps on moving, keeps on moving. So by doing that, we took two types of lamins. One normal lamin, we took another that's called wild type. We took another type of lamin, which is from diseased or mutated. Any disease means there's mutation, change from the original. And what we have here is that wild type lamin we took, and this was actually mixed with some buffer solution, and we trapped a small polystyrene probe inside this lamin plus buffer solution, and at different concentrations of this lamin plus buffer, basically this is what is changing. We measured this elastic component. Remember, there is a viscous component. This is the elastic component. This elastic component decides how hard or how stiff the lamin has become. So you can see that this was wild type. This is the normal one that you see naturally. This is the mutated one. And you see here that these are all three sets of data. But if you see for the high concentration one, wild type, 1.5 mg per ml, right? This is how the viscoelasticity or the elastic part evolves as a function of frequency, in the sense that so at different frequencies of my excitation, because I'm moving the probe at different frequencies, right? I told you that I'm actually using active microrheology, where I'm moving the probe by some preordained signal. So as a frequency of that signal, if I change, I measure this component. So you see, this is almost more than, this is like how much, 0.2? This is almost 2, 3, 4, 10 times higher. So the mutated lamin has 10 times higher stiffness than the wild type lamin, right? So I know from my tweezer, suppose I'm given a sample which I blindfolded, I don't know what it is. I measured the elastic component of the viscosity, and I find I have already calibrated a normal viscosity, viscoelasticity, or the solid component. And I know that at some 100 radians per second, it should come to some 0.3 or something, right? But I measured 3. So I know there's a problem. And just to ensure that this is really the case, our collaborators at, this is SINP, Kaushik Sengupta's lab, they did some kind of a SEM, scanning electron microscopy imaging, and they actually saw that this is the wild type, this is the mutated. You can see that these are like some kind of a mesh, okay, some kind of net protein, sort of lamins form some kind of a network. You can see that the average net size, mesh size, is much bigger here. So remember that if a net has very small pores, it's much more flexible. But if the net has big sort of mesh sizes, it becomes sort of hardish. So this method actually is able to tell you that the hardness of this material, this biological material, has changed when it has mutated. So if I can, for example, I'm given some patient sample, which has this lamins, which is extracted from maybe some cerebrospinal fluid or blood or wherever you can extract lamins from. And if I do a measurement, I can actually tell you there is a problem. There is a problem in the stiffness, right? So this is what optical tweezers can actually facilitate for you. Okay, so I think I've taken up a lot of time. I'm probably, I've overshot my time. So so I'm going to end here. So basically what I told you, so before I just end, let me just summarize once. I told you about how DNA sort of elasticity, how it twists and pulls, and stiffness and all that. You push and pull and twist the DNA. I told you about how kinesin starts sort of walking. These are very, very interesting applications. And I told you about how some kind of biological entity, the viscosity might change, and you might use optical tweezers to pick up this change in the viscosity. So before I end, I will just play for you this fantastic interview that Ashkin had given. So this pointer is creating a problem actually. So just hear this out. Can you hear this? Is this heard?
No.
Okay.
Yes.
Yeah, 1 minute. Let me just start again.
May I ask, are you still experimenting in your home lab?
I am. In fact, I'm writing a paper now that you guys are disturbing in my send it into science and hope that they'll accept it.
So basically what he said is that I'm writing a paper. So Ashkin was more than 90 when he got the prize. And he essentially said that you guys are disturbing me. Let me work. So this is a very, very famous piece of poem written by John Donne. For God's sake, hold your tongue and let me laugh. That was the original poem. So what Ashkin said was, let me work. He was more than 90. He was writing a paper when this is actually a sort of, this was some press which actually wanted to take his views after the Nobel Prize interview. So this interview essentially, he says, you're disturbing me, please let me work. Okay? And that is what he keeps on. That's what a scientist does. A scientist does not retire. A scientist keeps on working. So I end here, some pictures from the lab. This is the last picture, which is taken by about 3-4 months back. We have a group of 13 people at the moment. We have this person is left. Another person is going to submit his thesis today. So this person is leaving today, and we're finishing today, going to Japan. This person is going to Germany. We have some PhD positions. One wants to apply, please come here. Yeah, we'll be very happy about it. Yes, thank you very much. I'm open for questions.
Thank you very much, Professor Ayan, and it was a very nice talk, and we enjoyed a lot. The floor is open for few queries and questions. So if you have any question, you just please raise your hand and.
So should I stop sharing my screen, Rakesh, or should I keep?
Yes, yes, you can.
Okay. Sure. Yeah. So
Yes, Ram Baba Rajput.
Thank you, sir. Regarding the optical tweezers, so sir, you said that when the potential gradient is very steep, the
Yeah.
Brownian motion is very fast. Means
Very
the particle
very
is
small, and it's going to be frequency
fast
is very
oscillating.
Yes.
So I guess it will behave like an oscillating dipole. And
That is not necessarily. I mean,
means not in the
yeah, it's
bio
you can probably
samples.
say it. Yeah, you can say it.
Yeah. So what about that means radiating the radiation that the oscillating particle will emit?
So one little correction, Rambabu. This is not, so dipole is a very small thing, right? This is a sphere. So this is actually having millions of dipoles inside, right? So this is a particle which is a few microns big.
Yeah, so that is why I'm asking what means if it is not a bio sample, some charged particles, and they are oscillating inside this trap, and since they all are oscillating in the same frequency, I guess. So that
No, it will not be the same frequency. Also, you get a frequency distribution actually.
yeah, depending on the height, of course. Means
Yeah, you'll get a
profile.
frequency distribution.
So
You don't get the same frequency. Yeah.
So my question is there any studies related to this, means how this radiation which is emitted due to this, any
If you have a charged particle.
Yes.
If you have a, so this is an interesting question. So we had actually started some work on these charged particles, and see, the thing is that because the acceleration and all is very small, because remember this is in a overdamped case, it's in a fluid. So actually it's very, I mean, you know, the frequencies of oscillations are only of the order of, at very sort of best, they are like maybe a kilohertz or something. So it's actually not too much. But if you have a charged particle, then there are all kinds of nice things which come in the sense of the, you know, there are interactions with the environment changes quite a bit. So what you will find is, see, remember we are using light to detect. So the scatter pattern that is emanating from the particle that is trapped, that will change when the particle moves. So if you have a charged particle, on the other hand, then the interactions with the environment will change and the way the particle moves will change. Right? So from the pattern itself, you have some kind of a model to sort of fit that, then you can actually find some stuff. So there is work in this, where if you have charged particles and you know, look at different domains of interaction between the environment and the media outside, and especially if you have like fields, then there are things like long range interactions, short range interactions. These seem to change. So there are studies on the long range and short range interactions. If you want, I can probably, we had started some work on this, but it did not bear too much of fruit. There are papers I can probably send to you if you write to me personally.
Yeah, because actually I'm PhD student here in Pilani, so I just thought about this thing. Okay, thank you.
Yeah, sure.
Okay, any other question? Ready? I suppose there is no more other question. May I ask a question?
Sure,
Maybe,
please.
maybe now enough because
Please,
I'm not
please.
expert of this field.
Please.
But you were talking about the twisting of this biomolecule by this circularly polarized light, and then you measuring the intensity. And so nowadays we have this twisted photon beam.
Oh,
So they carry enormous angular momentum.
so you are talking about orbital angular momentum, right?
Yeah,
So there are
orbital
two
angular
types.
momentum.
There is spin angular momentum, there is orbital angular momentum.
Yeah, orbital angular
So
momentum.
orbital angular momentum tweezers is a very different story. That is very,
Okay.
very interesting. So
Yeah.
that creates actually orbital motion. So the particle will move like that.
Okay.
That's here it is spinning, right? Particle spins. So
Okay.
problem is if it's a circular particle, then if it spins, the trajectory doesn't change.
Okay.
Here, what you do is because the polarized light is the polarization is changing, you have cross polarizers in order to find out the exact change of the polarization, which you map with the trajectory, right? So the particle is spinning like this, the polarization is changing. So essentially, if you have two polarizers like this, then you will find out because circular polarization gets mapped to linear when you put a linear polarizer, and then the angle of that linear polarization is different. And then if you have a cross polarizer like this, then essentially the intensity at the output will change as you change the input polarization after the first polarizer.
So that is
from
related
that
to intrinsic.
yeah, spin. Intrinsic, yeah, kind of. Yeah. I mean, extrinsic
spin.
is, yeah, of course. Extrinsic essentially comes because of your, these orbital angular momentum or at the center of the gravity of the beam or something shifts, and then so you can have intrinsic orbital and extrinsic orbital. So the spin is always intrinsic. So that cannot be extrinsic spin that way. There are different spins though. There is this longitudinal spin, which is along the axis of the beam, and there's something called transverse spin, where it is along the axis of the beam. Those are very exotic stuff. So we are doing a bit of that in the spin orbit interaction work that we do, where we actually can try to look at this kind of spin, whereas spin is the normal thing that is seen. That is what they use in Kinesin walking and all.
Okay.
Yeah. So others, I don't think. I
So,
don't know. Yeah. Either people
yes,
understood
yes.
everything or understood nothing.
General comments, anybody wants to say? Yeah, I enjoyed your talk a lot because I'm not expert of this field, but the way
Actually,
you
I
presented,
tried to do it. You and
yeah,
understand
I
that
like the pedagogy aspect, especially the pedagogy aspect.
Yeah, that is
So
what I
enjoyed
tried.
a lot, and
Thank you.
yeah, thank you very much for this talk. And actually, I forgot to tell you about this Nobel Talk series and the department. I was supposed to tell you at the beginning of the lecture, but anyway, in this Nobel Talk series, we are organizing 5 talks. So we have organized two earlier talks. One was given by Professor Deepak Dhar. We were fortunate enough to catch
You got
him
the prize
before
very
he got
recently.
his Boltzmann Prize.
Boltzmann Prize, yeah, of course.
And the second was Professor Ghanshyam Date. And the third one was from yours. And we will have 2 more talks.
I am privileged.
So,
Acha, I actually,
so we
Rakesh,
will.
I forgot to put that reference. So I missed that reference somehow because this is the very reference that I'm putting for that Bastamante paper. So anybody who wants to do it can just look at it because this is a very, very nice reference that has come up in like 2021 Nature reviews. So that can be picked up. So if you really want because Nature Methods is it's like a cookbook recipe type journal. So you can really get every possible information you want from this paper. So this is just 2021. Yeah, so you can, whoever is interested can actually go and, read this paper up.
So we would be happy to receive you.
Sure.
We would be happy to host you in the offline talk.
Let's hope that happens soon.
Whenever you have time or you are in Delhi, please call us. And if the situation favors, we would be happy to host you in Pilani.
Thank you. It's been very nice, though. Of course, with the offline talk, I think the interactions would have been much better.
Yeah.
Thank you.
So with this, we can formally close this talk. Thank you very much again, Professor Ayan Banerjee.
Yeah.
See you.
Thank you. Take care.
We can disperse now.
Yeah. Let me just go. Thank you.